Hi. A very popular undergrad lab using a carboxylic acid is the Fischer esterification of salicylic acid to make methyl salicylate, which is wintergreen oil. It actually makes the lab smell pretty minty, and a lot of fragrances and flavorings are esters. So this is a nice lab to demonstrate that. Okay. I'm not going to discuss all the neat biology with these molecules. You know that salicylic acid is the precursor to aspirin. Methyl salicylate has actually a cooling effect on the skin, and that's why it's used in ointments like Bengay. Instead, I'm going to focus on how I would write up my notebook in preparation to do the lab, notably the Prelab entry and the Stoichiometry Table. So here I have the chemical structures, but I also have some information about the molecular weights. Methanol is a liquid, so I put its density and the amounts that I plan to use in the lab experiment. So I am going to go to a lab notebook, and all of this would be what I would write before entering the lab to run the reaction. Okay, let's start at the top. Okay, at the top, and this is what I expect my students to do before coming into lab. Definitely have a title, a page number, a date, then the chemical reaction. Now, I put a 1 here. In the actual drawing, or the electronic drawing, I have a bold 1, and that's how chemists typically notate their molecule, so they don't have to name it every time they mention it. Use a bold number. But sometimes it's hard to see whether a number is bold on paper, handwritten, so I usually put a squiggly mark underneath. I don't need an abbreviation for methanol. It's just CH3OH, so that's pretty short. And then here's my product. Okay, now I left this blank so far. This is theoretical yield. I'm going to show you how to calculate that, and we'll come back and we'll add it. The theoretical yield of product based on the amounts of starting material that I use. Also, at the beginning of the pre-lab entry, if the glassware is fairly interesting or it's a new technique, I usually draw it. We're going to do what's called a reflux. And this is the reflux apparatus. There's a condenser tube. I won't get into that. I do want to get quickly to the other elements of a pre-lab entry and the calculations for the stoichiometry table. But after your chemical reaction, a sketch of the glassware, if it's a new technique that you're doing. Next is the purpose. Okay, so here the purpose, it has to be straightforward. It has to be direct. What is your job in this experiment? Okay, what are you meant to be in lab for? To synthesize, wintergreen oil, methyl salicylate via Fischer esterification under reflux. So in a fairly short sentence, what did I do? I put exactly what we're going to do. Okay, I gave some name of a chemical. Okay, this is the name of the product. I gave the name of the reaction, or the reaction, the type of reaction. And I also gave a technique. So within this very short sentence, I gave, really 4 crucial facts about this experiment. Okay, so you try to touch upon the chemical name, the type of reaction, the technique, and yeah, exactly what you're going to do. You're there to synthesize wintergreen oil. After the purpose, I have the source. Now, my source, really the source of the procedure, is from a handout that I put on our learning management system. We use Moodle. Some of you out there use Canvas or Blackboard. Many times this would be a literature article, but I don't have the citation for that. It's been so long, and we've made so many adjustments to the procedure of this lab that basically it's very different than, well, not very different, but it is different than any literature procedure. Next, chemicals. Okay, so again, to recap, definitely if you're one of my students, pause, but we have the title, every good thing at the upper right corner, chemical reaction, drawing of the apparatus, purpose, source, now chemicals. What about chemicals? I'm only listing the main chemicals used in the reaction, which is the salicylic acid, the methanol, and the sulfuric acid. Okay, the starting material. I give the name, and I give the molecular weight, and I describe the material. Now, this white soft powder, this description, we may not know until you get into the lab. So you'll leave this blank until you see what you're working with. Same thing for the second starting material, methanol. You could definitely look up the molecular weight, the density, but wait till you get into lab before you describe the appearance, because maybe the chemical had degraded and now it's cloudy, maybe cloudy white liquid. You may push on and use it, and if it works, great. You have a record of, yeah, even if the methanol is cloudy and white, the reaction still works. That's why it's important to put the appearance of the chemical when you first see it, at the beginning of the lab. For the sulfuric acid, it's 3 molar, and I know it's a clear colorless liquid, but again, I wrote this after I saw it in lab, so I left this blank in my pre-lab entry. Okay, that's chemicals. Next is the big one. So far, that's the pre-lab entry. The next thing is the stoichiometry table, and this causes some concern with students, but let me try to walk through this step by step. Okay, there are 4 columns: compound, the amount. Eventually, you're going to want to get into grams because you need grams to figure out moles. But the mole amount is typically very small, 0.00259. So I'm going to multiply it by 1,000 to get the millimoles. All right, and then the last column it's called equivalence. Usually you just put EQ, but let me write the whole thing, equivalence. Sometimes I think it's equivalence. I'm pretty sure it's equivalence. Okay, and I'll show you how to calculate that. But the first thing is millimole. Okay, where did I get this 1.80 grams? It's from the procedure, and I also put it here on the chem draw. Okay, 1.80. Your molecular weight is 138.12. So this is how to figure out millimoles. 1.80 grams divided by the molar mass, or the molecular weight, 138.12. You see that number? 0.013. That's moles. So millimoles is times 1,000. Okay. It's a lot more millimoles because it's smaller. So you fit a lot more you have to fit 1,000 millimoles in 1 mole. Anyway, you move the decimal place 3 times to the right, 13.032. Let's just round to 2 digits past the decimal. 13.03. Okay, that's actually quite a bit. How do we do the methanol? You notice the amount given was in milliliters of volume. Well, within the stoichiometry table, I'm going to convert that into grams using the density. So it's 4.50 milliliters times 0.792 grams per milliliter. So the milliliters cancel out. And I got grams 3.5, whoops. Do you see that? 3.564. Did I round? Yep, 3.56. So you want the amounts in grams, because then you could take that number, go ahead and not round, just keep it in a calculator, because we're going to divide by the molecular weight, 32.04. And that is the nope, that is the moles. That's the moles times 1,000. So the millimoles is actually large, 111. Do you see how much larger, though, it is to the millimoles of salicylic acid compound number 1? Let me just finish this. 111.24. That's already the units, so I'm not going to put the units here. It's 111.24 millimoles. Now, I have a row for the product. Okay, we'll fill that out in just a bit. And what is this equivalence? It's really based on the moles, and it's the parts. For every 1 part of 1, I have this many parts of methanol, or vice versa. For every 1 part of methanol, I have this many parts of 1. But the convention, I think, for most scientists is, what is 1? What are we going to count as 1 equivalence? Are we going to count it as this starting material, this starting material? You're going to figure out which one is the limiting reagent or the limiting reactant, and you're going to set that to 1. So not in your notebook, okay, this is the Prelab entry, but on a scratch sheet of paper or on, I reserve the left side of the notebook for calculations. We're going to figure out which one of these two is the limiting reactant. Now, sulfuric acid is in excess, okay, so that was probably written in the procedure, but also it's really just a helper molecule, or I'll say catalyst, but we use this in much more excess than the other 2 reagents. So we're not going to count that as a possible limiting reactant, and it's not. Okay. Where are my limiting reactant? Oh, there it is. Here are my limiting reactant calculations. The idea is, if all of 1 is consumed, how much product do I make? And we're going to compare that to if all of 2 is consumed, how much product that makes. And then you're going to pick the smaller amount. That's the limiting amount. You can't make any more than that because the reagent had run out. So let me show you how I would set that up. Now, again, this is not in my notebook. This is on a scratch sheet of paper. But let me see if I could do this stepwise. Okay. So the first set of calculations is pretend that number 1, the salicylic acid, is the limiting reagent. 1.80 grams of 1, and it is essential that you have the 1 here. Okay, you have the compound. We got into moles before, and that's just by dividing by the molar mass, or the molecular weight. The grams cancel out. So I have moles now. We're going to use what's called the mole bridge, okay, to go from, that's why it's important that you have this compound 1 here, because now we're going to cross using the mole bridge over to the products, because I want to know theoretically how much product I would make if all 1.80 grams of salicylic acid is consumed. Now, where is this coming from, this 1-to-1? In general chemistry, it was pretty easy because you were given the molecular formulas, and it was easy to tell, how many atoms of a reactant end up in the product. But with organic chemistry, you have to figure out which part of the product came from where. And you may not know the mechanism of this reaction yet, but I'll tell you here that this part right here comes from the methanol. Okay, so it looks like we take 1 molecule of salicylic acid, the proton is actually, the OH is removed, and we add CH3O from methanol. What does that mean? The bottom line is it's a 1-to-1-to-1 ratio. So for every 1 molecule of this, theoretically I get 1 molecule of product. For every 1 molecule of methanol, theoretically I get 1 molecule of product. Now you may ask, well, isn't that obvious? No. Sometimes you could have a molecule where you can append 2 methanols, in 2 different sites. But we're not going to do that here. We're only going to append or add 1 methanol to salicylic acid. And that will make more sense once you learn the mechanism in lecture. Okay, so what was it that all that discussion about? All that discussion was about figuring out this, we call this the mole bridge, how to cross over to the products. It's a 1-to-1 ratio. All right, and then since we have moles of product now, we're going to convert it to grams of product, and that's my grams of product, 1.98 grams. Okay, that's theoretical if all of this is consumed, meaning that if we have an unlimited amount of methanol. Now let's go the other way. What if methanol is the limiting reactant and we have unlimited amounts of number 1? Okay, so we're going to use up all the methanol. Well, we started out with 4.50 milliliters. Okay, so we don't even have grams. We have to convert to grams using density. Oh, I don't want to give away the answer. Okay, and then we need moles. So now we have divided by the molar mass or the molecular weight. Sorry, I keep saying molar mass because that's what my general chemistry students use, but organic chemistry students use molecular weight. And therefore now I have moles of methanol. So I need to use a mole bridge to get over to the product side. And there is the mole bridge. And again, it's 1-to-1 ratio. And then I have, thus far I have now moles of product. So times the molecular weight, almost did it again, of the methyl salicylate. Right, this is the molecular weight of our product. And I get 16.92. Okay. So what this means is that now that we're using these amounts, okay, for the reaction, we know that the maximum amount that can be gotten once this is all used up is 1.98 grams. So once 1.98 grams is reached, we have no more of salicylic acid. Okay, we have a lot of methanol because it could go up to 16.92 grams of product made. That means 1 is the limiting. It runs out first. And not only that, this is the theoretical yield, Ty. So let's, before we forget, let's put that here. It's actually really good to know beforehand how much product you expect to get. So this is 1.98 grams. 1.98 grams. That I want my students to put because you want to have an idea. You know, if you have like a little pinch of the product, you want to know, is that what I expected or is that way too little? Or more likely, if you have a product that weighs 10 grams, well, something definitely went wrong because there's no way you could have made 10 grams of product from these amounts. Okay, and then since you know something's wrong, you could correct it. Maybe it's impure. Maybe it's heavy because it's wet with solvent. You could make the adjustments if you knew what the theoretical yield is. Okay, where's this discussion leading to? We got to get back to the notebook. This is all scratch paper. The notebook, I'm missing the equivalence. It's parts. So here's the rule. Once we found the limiting reactant, right, my conclusion is 1 is a limiting reactant. You're going to make that compound equal to 1 equivalence. I should have wrote that down here. The limiting reactant is set to 1.0 equivalents. Okay. So now we can say for every 1 equivalent, do that right now, that's the limiting reactant or limiting reagent. And I'll put a little reminder here. For every 1 equivalent of compound 1, how many equivalents of methanol do I have? This is just a ratio, all right? So I'm going to explicitly show you the calculations because it's kind of, for me, it's unusual why students get this wrong a lot of times. Okay, let me go over the calculations. So it's a ratio of the millimoles. Okay, so we're not worried now about any coefficients in the reaction. And anyway, for now, for us, it's 1 to 1 to 1. It's a ratio of millimole equals a ratio of the equivalents. So literally, this is your calculation. Because we have 1 and we have methanol. Let's take the ratio of the millimoles, 13.03. So I'll put a little divisor sign, 111.24 equals 1.00. You are solving for x. That's it. So it should make sense. It kind of confuses me. Why would someone put a smaller number here? I'm not sure what calculations they're doing, but a lot of times I see a smaller number here. Well, if one equivalence equals 13.03 millimole, x equals 111.24. What is x? So you're solving for this equation. What do? We want to cross multiply 111.24 times 1 divided by 13.03. Okay, so I got x equals 8.54 equivalents of methanol. Why is this a column? Why are we interested in this? 8.54. Because this tells me how much excess methanol I have. It's not a 1-to-1 ratio like the reaction would have predicted. If everything was perfectly balanced, we'd have 1-to-1. Now, there are reasons why methanol is used in excess, because it's also a solvent, but also we're applying Le Chatelier's principle. I'm not going to get into that. Okay, we're just worried about the Prelab entry and the stoichiometry table for now. So that is done. That's the equivalence. Now, what do we do for product? Well, we figured out. We figured out the theoretical yield. So we'll put it down here, 1.98 grams, but put a little reminder. This is a theoretical yield. Okay. Why? Because it came from the fact that 1 is the limiting reactant. So we would expect that we would get 13.03 millimoles of product, but again, that is theoretical. So we'll put theoretical yield too. A yield is an amount, either in grams or in moles or millimoles. If everything works out perfectly, then this is how much you should get. 13.03 millimoles, which equates to 1.98 grams of product. Okay, it's not going to be 100%. There's always some lost product and there's some inefficiencies. And actually, this reaction is reversible. Okay? I'm sure your lab instructor or your lecturer professor will talk about that. The very last thing before entering lab is in the pre-lab entry, you want to have the procedure in numbered or bullet steps. I'm not going to do that in the video here. And then at the very end, you put observations and 1, and that's it. This is blank until you start doing the experiment. So that is the pre-lab entry. Let me zoom out a little bit. This is what I expect students to be able to do before coming into lab. Okay. Make note of all the different sections and what I want for purpose, what I want for the, I call this the cartoon and the chemical reaction, and finally the stoichiometry table. We only included the compounds that were used to determine the limiting reactant, so I don't have the sulfuric acid here because sulfuric acid, I told you, was in excess already. You have the reactants that are dealt with in the limiting reactant calculations and the product. Okay. Now, for my students, if they forget at some point in the semester, what goes in pre-lab entry for a reaction, I want them to refer to this video.